Good evening, everyone. Welcome to NPTEL tutorial sessions on the course Principles of Organic Synthesis. So, here we have the week 5 tutorial session. So far, we have seen the 4 weeks tutorial sessions which were on the formation of aliphatic carbon carbon bonds, base catalyzed reactions, formation of aliphatic carbon carbon bonds, acid catalyzed reaction, organometallic reagents and organometallic reagents and organomagnesium reagents, organolithium reagents. This were the last week's topic of discussion, and we have also solved some problems based on that, and as well as we saw the solution for the week 2 assignment questions also. So, in this week 5 lecture contents, we have seen the reactions of some other organometallic reagents other than organomagnesium and organolithium. That was organocopper, organozinc, organomercury reagents. And also, we have seen some reactions involving the formation of aliphatic carbon nitrogen bonds. So, first, we will see an overall outlook of what we have seen in the organometallic reagents topics, that is organocopper, organozinc, and organomercury reagents. So first of all, we have seen this Gilman reagents, which are basically organocuprates. And organocuprates are mainly used for the conjugate addition. Conjugate addition means one for addition rather than one to addition. There we can also say that like if there is a alpha beta unsaturated carbonyl compound, this carbonyl carbon center we can call it as a soft center, and this beta position to this carbonyl group we can call it as a hard center. So if we are using Grignard reagent or organolithium reagent, it will be their soft nucleophiles and they will be preferring the soft carbonyl center. But on the other hand, if we are using this Gilman reagent, it is a hard nucleophile and it will be attacking at this center over this center. Okay, so here it is given already. Gilman reagents are excellent nucleophiles to form carbon-carbon bonds. So they are used in this conjugate addition. Otherwise, we can call it as one for addition to alpha, beta, unsaturated ketones. So Grignard and organolithium reagents will add to ketone in this case. So it is going through this mechanism. First, uh, this methyl group or whatever alkyl group is there, that will attack over this beta position, and simultaneously this lithium enolate will be formed, and then mild acidic workup will give this ketone back with this conjugate addition product. Then another one reaction which we saw for this organolithium compounds was this reaction of this alkyl halides with organolithium compound, where this halogens will be replaced with this alkyl group. Similarly, in the case of acid halides, we can use this organolithium reagents to form ketones. So the main thing which we have to remember is that using Gilman reagent or organocopper reagents, one for addition will be preferred over one to addition. Now then, yeah, this is one mechanism which we already discussed. So this nucleophile is a pair of electrons in this copper carbon bond, so that will attack over this beta position. This bond will shift to here and this will become O minus, which will be stabilized by the Li plus from the organolithium organocopper compound. So this enolate can exist in this resonance form, and then during acidic workup we will get this conjugate addition product. Now we will see some of the reactions which we saw in the lecture 9, that was regarding organo copper reagent. We have seen the Glaser coupling and Castro-Stephens coupling. So Glaser coupling is basically the homocoupling reaction of two terminal alkynes in presence of copper salt and pyridine base. So the mechanism is like this. First, the base whichever we are using, that is pyridine, will take up the proton of this terminal alkyne, forming this particular carbon ion and this protonated pyridinium ion, and then this carbon ion can react with the copper salt we are using. Here we are using copper 2 acetate and form this copper acetylidene complex, and then it will react with the second molecule of this copper catalyst which we are using, and it will form this radical, and then this radical will undergo homocoupling with another molecule of the same like another same radical of another compound to form this homocouple product. So that is Glaser coupling. It is basically homocoupling between two terminal alkynes in presence of copper and pyridine. Then the another reaction which we saw, which is mediated by this organocopper reagents, is Castro-Stephens coupling. So Castro-Stephens coupling is a cross-coupling reaction between this copper acetylide and aryl halide. So instead of homocoupling, what we are using here is an aryl halide, and pyridine also we are using. So this is basically generated by the reaction of this terminal alkyne with copper, and here we are also using an aryl halide. So in presence of this pyridine under heating condition, it is forming this couple product, and copper halide will be the byproduct. So the mechanism is like that. First, this copper halide, acetylidine complex and this alkyl halide will undergo oxidative addition over this copper to form this particular complex, and then this, yeah, like reductive elimination, we can tell reductive elimination kind of step occurs to get this couple product. So that is the Castro-Stephens coupling, which is basically the coupling between aryl halide and a copper acetylide to form a disubstituted alkyne. Then, coming to organo-zinc reagent, we have seen this Reformatsky reaction. So it is basically the reaction between this alpha bromo ester. In presence of zinc and acidic condition, we will get this beta hydroxy ester as a major product. So the mechanism of this Reformatsky reaction is given here. So first of all, this alpha halo ester, which will react with zinc to form this Reformatsky enolate. That is, the zinc will undergo oxidative addition, we can tell, and this will form this ZnBr, this complex. Then what is happening? It can form this an intermediate with this another molecule of this particular compound, and it will be existing in this intermediate structure. Then we can tell, like, this when there will be interaction between this oxygen and zinc, as well as zinc, this oxygen and zinc of another same molecule, and that oxygen and zinc of this molecule, so that will be resulting in this intermediate. Then what is happening is this bond will shift to here, this bond will shift to here, and this bond will shift to here, and we will get this type of enolate, that is oxygen zinc connected enolate we will be getting. Then in the presence of this ketone, what is happening is that that enolate will be attacking this carbonyl carbon of this ketone, and we will get this six member transition state. And then, upon acidic workup, then the zinc bromide will be leaving to get this beta hydroxy ester. So that is basically Reformatsky reaction. So Reformatsky reaction is the reaction between this alpha halo ester to give this beta hydroxy ester using zinc. So it is an organo zinc mediated reaction. Now moving to another zinc mediated reaction, which is Siemens-Smith reaction, which is basically used for the cyclopropanation reaction. Here we can use zinc and this dihalo uh, dialkyl compounds and zinc copper couple. So here what is happening is that just cyclopropanation is happening. That is, this will attack over this, and this will attack over here to form the cyclopropane ring. So it is basically, the mechanism is through a carbene intermediate, we can tell. So first, this CH2I2 in presence of zinc, it will form this intermediate, and then in presence of alkene, what is happening? This will attack over this, and then here carbene is actually generated, so that carbene can attack over this, and this position will attack on the carbene to form this particular intermediate. Then zinc iodide will be leaving as a stable molecule to form the cyclopropanated product. Okay, now so that was the Siemens-Smith reaction. Then another reaction which is mediated by zinc organo zinc reagent is Negishi coupling. Negishi coupling is basically the reaction between this aryl halides or halides and this zinc compound, organo zinc compound, in presence of palladium or nickel to give this coupled product. So it is basically a coupling reaction. So here what is happening is that initially the electron rich palladium zero catalyst inserts into RX bond. That is, this our halide whichever we are using will undergo oxidative addition into this palladium complex to give this compound. Then whatever organozinc reagent which we are using, that will undergo transmetallation to form to leave this zinc halide, and we will be getting this particular intermediate. Then yeah, before the reductive elimination is taking place to get this coupled product, next step will be the isomerization to bring the organic ligands next to each other into cis position. So first this both R group should come to cis position, then only reductive elimination will be possible. Then the reductive elimination will be taking place to form the cross couple product while regenerating this palladium catalyst. So it is a coupling reaction between halides and organozinc compounds in presence of palladium or nickel also we can use as the catalyst. Now, so that's all about organo-zinc reagents. Now we have seen organo-mercury reagent mediated reactions, which is basically oxymercuration, demercuration of alkenes, where this alkenes will react with this mercuric acetate or mercury 2 compounds to form this alcohol as the product. So here what is happening is that this first the mercury, this alkene will be reacting with this mercury acetate to form a three membered, that is here, yeah, here it is given, this mercurinium ion will be forming in the first step, and then what is happening, which undergo attack by the solvent. So water molecule can attack over this center, and this will transfer to here, and it will be forming an anti-addition is taking place. Then this mercury we can remove by demercuration by using NaBH4. It will remove, that is this hydride will be coming and attacking over this carbon, and this HgOAc will be leaving out. So we will be getting alcohol. So here these are the some of the points that we should be um, aware of while carrying out this oxymercuration demercuration reaction. First, the nucleophile adds to the most substituted carbon of the alkene. So, where this incoming nucleophile will be adding, it will be adding over that is water in this case. So, it will be adding over the most substituted carbon of the alkene, that is Markovnikov's regioselectivity will be there. So if we are using alcohols in presence of water, we will be getting ethers. That is, to open this mercurinium ion, if instead of H2O, if we are using any alcoholic source to open this mercurinium ion, we will be getting ethers instead of alcohols. That is, here OR will be there, that case. Then in some cases we can even obtain rings also as a result of this oxymercuration demercuration reaction. So this another thing is that the removal of this mercury by using demercuration step, that is by using NaBH4, it proceeds through a radical mediated step, so that the stereochemistry of this reaction is not at all under control. This process is not stereoselective overall. So that's about the oxymercuration demercuration of alkenes. Now, yeah, that was about the reactions of organocopper, organozinc, and organomercury reagents. Now, moving on to the reaction, we have seen here Ritter reactions as well as Gabriel synthesis, especially for the formation of carbon nitrogen bonds. So, carbon nitrogen bond can be formed in two ways, either by the reaction of a nucleophilic nitrogen with electrophilic carbon, or by the reaction of a nucleophilic carbon with electrophilic nitrogen. Okay, so the first reaction which we saw for this carbon nitrogen bond formation was Ritter reaction. So Ritter reaction is basically the reaction between alcohol or alkene, we can say, in presence of acid and this nitrile, followed by workup we will get this amide. So what is happening here is that the reaction is proceeding through this stable carbocation. So here as we can see the mechanism, if we are using alcohol in the presence of acid, first it is getting protonated to form this intermediate. Then by even elimination, one molecule of water is leaving out to form the stable tertiary carbocation. Then since we are using this nitrile compound, that lone pair of nitrogen can attack this positively charged carbocation to form this particular intermediate. Then what is happening is that this carbon nitrogen bond will be shifting here to stabilize the positive charge on nitrogen, thereby forming a carbocation, that is this particular compound. Then one molecule of water, which also we are using in the reaction medium, will attack over this carbocation to form this compound, then proton transfer is occurring, that is, yeah, one proton will be leaving as H3O plus in presence of water, and we will get this. Then these are basically, we can say, tautomers. So this is in the enol form and this is in the amide form basically. So that is a Ritter reaction. So it is basically used for the formation of carbon nitrogen bonds, where we can convert alcohol or alkene into an amide by using acidic condition and nitrile salts and water, and it proceeds to a stable tertiary carbocation intermediate. Now, moving to the last thing which we have seen in the week 5 lecture videos, that was Gabriel synthesis. So, it is basically a method for the formation of primary amines. So, here the product is primary amine by the reaction of a phthalimide salt with an alkyl halide. So, here this phthalimide group, what is the advantage is that it will prevent the nitrogen from undergoing multiple alkylation. So, yeah, and the first, when treatment with a base followed by this alkyl halide, we will be getting this compound. Then we will treat it with this hydrazine, and in that case, what is happening? This primary amine is formed. Yeah, so first we need a base, then alkyl halide, this phthalimide and hydrazine. Under heating condition, we will be getting this primary amine. So that's all about the discussion on the week 5 lecture contents. So we have seen this Gilman reagent, what are its use, how to prepare Gilman reagents, how it is different from other organometallic reagents, organomagnesium reagent or organocopper reagents. Then we have seen the organo-copper mediated reactions, that is Glaser coupling and Castro-Stephens coupling. Then we have seen the reaction carried out by organo-zinc reagents, that is Reformatsky reaction, Siemens-Smith reaction, Negishi coupling. Then we have seen organo-mercury catalyzed reaction, mediated reaction, that is oxymercuration, demercuration of alkenes. Then for the formation of carbon-nitrogen bond, we have seen this Ritter reaction as well as this Gabriel synthesis. Now we will be moving on to the discussion on some questions regarding these topics, whatever we discussed today and whatever we saw in the week 5 lecture videos. So the first question is, predict the major product of the following reaction. So here we are treating this compound with this CH2I2 in presence of zinc copper couple, which will be the major product out of the four options given below. So I'll give you some time to think what, which reaction it is. Basically, it is obviously a named reaction, and then what is the mechanism of the reaction. So from the reagents itself, it is pretty clear that it is a Simon-Smith reaction. So here what is happening is basically a cyclopropanation, and there is no other questions or doubt in this because there is only one alkene over here. So it will be, the correct answer will be option D, that is Simon Smith reaction. So the mechanism I have given here so that you can go through that once more. So this alkene first will undergo this reaction with this CH2I2 and zinc copper to form this disubstituted cyclopropane. So the mechanism is like this. First it will form this intermediate, then this center it will generate the carbene. So that will attack here, and this center will be attacking over that carbene to form this three-centered butterfly type transition state. Three-centered butterfly type transition state. Then the zinc iodide will be leaving to give the cyclopropanated product. So here the cyclopropanation will be happening. So the correct answer is option D. Moving to the next question. The major product of the following reaction, that is we are treating with this particular alpha beta unsaturated carbonyl compound with this higher order cuprate it is. So it is basically an organocopper reagent. So what will be happening? So out of the four options given here, which will be forming? So here, since we are using an organocopper reagent, and in the reactant there is an alpha beta unsaturated system, so what will be happening here? This group will be attacking over this center rather than this center. So we will be getting the 1,4 addition product, or we can say we will be getting the conjugate addition product. That is, the correct answer will be option C. I hope it's clear. So whenever we are using an organocopper reagent, that is Gilman reagent, we can say. So this is a higher order Gilman reagent which will give more selectivity and more reactivity compared to normal Gilman reagent. So it will be giving 1,4 addition product rather than 1,2 addition product. Moving to the next question. Yeah, here I have shown the mechanism. Like what is happening is that, so this is our organocopper reagent. So this copper minus will be attacking over this beta position. This bond will shift to here and this bond will shift to here. So it will be existing as this lithium enolate. Then this methyl group will attack over this, and this methyl copper group will be leaving to form this particular compound, which is also enolate, lithium enolate, which upon workup will give this enol, and that is which is the tautomer of, we can say, this ketone. So that is basically the mechanism of 1,4 addition reaction. I hope it's clear. We have seen many examples in the lectures as well regarding this 1,4 addition. Now moving to the next question. The major product of the following reaction, this alkene, and we have this nitrile over here in presence of H2SO4 and chlorobenzene, which will be the major product out of the four compounds given here. So this is also a named reaction which we saw in the lecture. First try to identify which reaction it is, then what is happening, which mechanism it is going through, and which will be the product. So which reaction it is? This is basically an example for Ritter reaction. So what is happening here is that I will change it to pen. Yeah. So what is happening here is that first this H plus from this acid will be taken up by this alkene. So H plus will be taken by this alkene to form a carbanion over one of the sender. Then what is happening once this not carbanion, carbocation is formed at the center? That is, alkene is getting protonated and carbocation is resulting. And then what is happening is that this nitrogen lone pair will be attacking over this carbocation center. So it will be basically like this. So this double bond already gone because it got protonated, and once that nitrile group will be attacking that center, it will be N. Here one positive charge will be there. Then this triple bond C and this vinyl group over this carbon. Then what is happening? So in the next step, what is happening is that this bond between one of the bond between this nitrogen and carbon will shift to here, so that this positive charge on this nitrogen is getting stabilized. But what it will be resulting? So it will be, sorry, yeah. So it will be basically resulting in this particular compound here, N double bond C positive, here this vinyl group. Then since H2SO4 means it is aqueous condition only, then one molecule of water will be attacking over this carbocation to form OH2. Then in presence of water, H3O plus will leave to form COH, that will tautomerize to give the particular amide. So out of this four options given here, the correct answer is option A. I hope the mechanism is clear. So answer is option A, and this is an example for Ritter reaction. So what is happening first? First this alkene is getting protonated, so one carbocation is formed, and this nitrogen lone pair will attack over that carbocation. Then that bond between carbon and nitrogen will shift to nitrogen to stabilize the positive charge resulted in the nitrogen, resulting in a carbocation. Then one water molecule will attack over that positively charged carbon. Then some elimination of one water molecule in the H3O plus in the presence of water molecule and rearrangement into its amide form will be resulting in this particular compound. So this is an example for Ritter reaction. Moving to the next question. So here also we can see this particular compound is treated with this tertiary butanol in presence of H2SO4. So which will be the major compound and which reaction it is? So this is another example for this Ritter reaction. So here also what is happening, first this tertiary butanol will get protonated and that OH2 will be leaving to form this carbocation over that tertiary center. That is a tertiary carbocation will be formed. Then this nitrogen lone pair will attack over that carbocation, and then again whatever we told same water molecule will be attacking over the carbon center, and positive charge on nitrogen will be stabilized to form the particular amide. So the correct answer is option C. So this is also an example for Ritter reaction. Moving to the next question. The major product of the following reaction. So here this compound is treated with this bromoester, alpha bromoester compound in presence of zinc and THF under reflux condition. So which will be the reaction, what is its mechanism, and which will be the product here. So which reaction it is and which is the product here. So this is an example for Refermatsky reaction, which is catalyzed by organozinc compound. So here what is happening is that first this zinc will get inserted into this, and this will be like ZnBr. Then we can tell this carbon will be attacking, or that will be negatively polarized because it is attached to zinc. It will be attacking over this center, and this bond will shift to here, and we will be getting this as the major product. So this is actually leaving out. The sulfur group is actually leaving out. So it will be CH2 CO2 Me. Mechanism I think we have already seen here. So I didn't include, I guess. Yeah, it is here. So what is happening is that first zinc will undergo this addition over this to form this particular compound. So this will be basically in the form of this, that is double bond O Zn Br, and here OE. Then what is happening, this will be attacking over this particular sulfur, whatever I showed here, that's ender, and this will be like, then this sulfur can coordinate with the zinc of the second molecule, and that sulfur, that oxygen can coordinate with the zinc, so it will form this kind of an intermediate, and then presence of H2O, it will be forming this compound. So once it is formed, if there is a possibility for elimination, this water molecule will be leaving out, and we will be getting this alpha beta unsaturated ester as the major product. Okay, so this is an example for Reformatsky reaction. Moving to the next question, predict the major product of the following reaction. So this, here one side ester is there, one side acid chloride is there. So here we are treating with this dimethyl copper lithium complex, which will be the major product here. So here what is happening is that in presence of this organocopper reagent, that is Gilman reagent, can undergo addition over acid chloride to form the corresponding ketone. So what is happening is here is that this methyl group from here will be attacking over this carbonyl carbon center, and this bond will be shifting to here. So once this bond will come back to here, the Cl minus will be leaving and we will be getting this ketone. So it is not attacking this ester at all, only this acid chloride is reacting with the Gilman reagent. So one thing you have to note down here is acid chloride can react with Gilman reagent to give the corresponding ketone as the product. So the correct answer is option B. Moving to the next question, the major product of the following reaction. So this compound upon acidic condition, which will be the major product out of this four given here. So this is also an example for Ritter reaction. So here also this amide is forming, but here one difference is that it is intermolecular, not intermolecular, intramolecular Ritter reaction. So here the correct answer is option B. B, right? No, option A, because in option B the stereochemistry has changed of this vinyl group, but this is a fixed chiral center, so its stereochemistry it's not changing at all, and the correct answer is option A. So what is happening here is first in the presence of H plus acid, this OH will get protonated. It will knock out as H2O plus, and here a carbocation will be generated, and then this nitrogen lone pair from this nitrile group will attack over this center, and then one water molecule will be attacking over this carbon to form the resulting amide. So the this is an example for Ritter reaction, and it is an example for intramolecular Ritter reaction, and the correct answer is option A. So moving to the next question, predict the major product of the following reaction. So here actually this reagent is wrong. Here we are using a Gilman reagent, that is dimethyl copper lithium complex Me2 CuLn. So this is the reagent. So when we treat this compound with this dimethyl copper lithium compound, which will be forming. So here what is happening is that first this methyl, that is Me minus methyl group, will be attacking over this alkene, and this bond will shift to here, and this will be leaving out. So that is what is happening here. Methyl group will attack over this center, this bond will shift to here, and this will knock out. So which will be the correct answer? Correct answer will be option A. Yeah, bond also shifted, this group left, and methyl group is coming here. Not option A, it will be option C. Moving to the next question. Predict the major product of the following reaction. That is, we are treating this alcohol with this nitrile in presence of acetic acid and H2SO4, which will be the major product. So this is also an example for intermolecular Ritter reaction. So here also what is happening is that in presence of this acid, this will get protonated and it will be forming this OH2 plus, and it will be leaving out as a water molecule. Then this nitrogen lone pair will be attacking over the carbocation forming at this center. Then one molecule of water will be attacking over the resulting carbocation of this carbon to get the corresponding amide. So we have seen today many examples including Ritter reaction. So here the major product will be this one, option D. So this is also an example for the formation of carbon nitrogen bond. Here this carbon and this nitrogen bond. Okay. Now moving to the last question of involving these topics of week 5 lectures. Predict the major product of the following reaction. So this compound in presence of this tin chloride and acetonitrile, which will be the major product out of this four options given here. So here the major product of the reaction is this one. So the correct answer is option D. So here what is happening is that first in presence of SnCl4, which is a Lewis acid, it will take the Cl minus, and here one carbocation will be generated. To that, what is happening, this nitrogen lone pair is attacking over this carbocation to form this intermediate, and then again what can happen, this one of the bond can attack over this center and thereby stabilizing this positive charge on nitrogen, and then regaining aromaticity we will be getting this particular compound. So that's what is happening here. Correct answer is option D. This we can say it's a modification of Ritter reaction, where, or not Ritter reaction exactly, but it's type of a modification where we are using nitrile also, and it is forming through a carbocation. So so far we have seen the reactions involving organometallic reagents, especially organocopper, organozinc, organomercury reagents, and then we have seen the carbon nitrogen bond forming reaction, many examples, that is Ritter reaction. So that's about the discussion on organometallic reagents. Now we will be seeing the week 3 assignment questions, because the due date is already over, and the solutions till week 3 assignments have also been uploaded in the portal, NPTEL portal. So we will see today the discussion on week 3 assignment question, which was basically on Manish reaction, Friedel-Crafts reaction, Prince reaction. So the first question of week 3 assignment was the major product of the reaction. That is, here one ester group is there, here acid chloride is there, and we are using ethene and aluminum chloride in the first step, and in the second step NaBH4. So which will be the major product? Okay, so here what is happening is that first, since we are using ethene, which is basically this one. So what will happen is that in the presence of this Lewis acid, the Cl minus will be living as AlCl4 minus, and then this cethene will be attacking over this carbon to give here carbocation will be formed, which will be quenched by the Cl minus from the AlCl4 minus to form this compound first. Then in the presence of NaBH4, which will not reduce ester, only this keto group will be reduced to give this compound. So the correct answer is option B. So what is happening is that first this double bond will attack over this carbon, Cl minus will be leaving out, and here will result in one carbocation, which will be stabilized by the attack of one Cl minus from the AlCl4 minus, that will be resulting in this compound. Then NaBH4 reduction of this ketones only will give the compound, that is option B. Moving to the, yeah, it is given here. It involves alkene addition to the acyl chloride followed by selective reduction of ketone to produce alcohol. Moving on to the second question, the major product of the reaction. Here we are treating this carboxylic acid with PPA at under 100 degrees Celsius, which will be the major product. So PPA is basically polyphosphoric acid. So which will be the major product in this case? Okay, so here what is happening is that basically in presence of this polyphosphoric acid, we can say this is the correct answer. So what is happening is that this polyphosphoric acid will take up this OH minus ion, and it will be resulting in this particular intermediate, and upon this is an intramolecular Friedel-Crafts acylation, we can tell. This bond will attack over this center, and this will come over here to form this. Then deprotonation will be resulting in the regaining of aromaticity to give this compound, that is option A. So the correct answer is option A, and this is an example for intramolecular Friedel-Crafts reaction, Friedel-Crafts acylation. Moving to the next question, the major product of the reaction. So first we are treating this compound with pyrrolidine in presence of formaldehyde and HCl. Then in the second step with methyl iodide and NaOH, which will be the major product. So this may be these questions you have already solved and you have already gone through the assignment solutions as well. So we will quickly go through this. So here the correct answer is option B. So what is happening here is that first this pyrrolidine, which is basically this one, will add upon this ketone to form this intermediate in presence of HCl. Then on the same at the same time, this particular compound, this ketone, this HCl will be protonating this ketone to form this intermediate, that is this enol will be formed in presence of acid. Then this lone pair of electrons will come back and this double bond will be attacking over this carbon center, and this positively charged nitrogen will be stabilized, so that will be resulting in this particular intermediate. Then in the presence of methyl iodide, this nitrogen will get methylated to form this quaternary ammonium compound, and in the presence of NaOH, it will be abstracting this acidic proton from here, and therefore that will be existing as this stable enol. And then when this lone pair will be coming out, this bond will shift to here and this group will be leaving by E1CB mechanism, and we will be getting this compound as a major product. So first step is the formation of iminium ion using this formaldehyde and pyrrolidine. Then that iminium ion will be this first ketone will form this enol, and that it will attack upon that iminium ion to form this. Then in the presence of methyl iodide, this iminium ion will get methylated to form this quaternary ammonium, and then in the presence of NaOH, base will abstract this proton, and when it will come back, it will leave this group through the C1CP mechanism, and we will be getting this compound option B as the major product. Moving to the fourth question, the major product of the reaction. So here one acid group is there and here ester is there. So in presence of aluminum chloride, which is a Lewis acid, which will be the major product of this reaction. So this is also an example for Friedel-Crafts acylation reaction. So here what is happening is that first in presence of aluminum chloride, this oxygen will be coordinating with this aluminum chloride to form this intermediate, and then what is happening, this lone pair will be coming over here and this will be stabilizing this oxonium ion to form this species will be leaving out, and we will get this one. So once this electron pair between this oxygen aluminum bond will shift over this center, this bond will shift over here and this center will be attacking this carbon, and this positive charge on oxygen will be stabilized to get this. Then upon regaining aromaticity, we will be getting this. So it is basically acylation, Friedel-Crafts acylation reaction, where this first it is leaving out, and then that itself is attacking over the center and acylating. Moving to the next question, the major product of the reaction. This compound we are treating with this aluminum chloride benzene in first step, then HBr 48% in second step, and then third step ammonia and isopropanol, which will be the major product. So here what is happening is that this is the product, that is this particular compound. So it is going through this mechanism. So first, in the presence of benzene and AlCl3, this AlCl4 minus will be leaving out, resulting in a carbocation over this center, and then benzene will attack over this carbocation, and that will form the species. Then when HBr is attacking, that is first in the presence of HBr, this is getting protonated. So first the intermediate will be this OH. Once it is protonated, and here phenyl group is there, then this Br minus will come and attack at this center, and this will open up to form here pH, and here, so here will be Br, and here will be OH. Now what is happening is that again this Br minus will attack all over that alcohol carbon center in SN2 fashion, and this OH minus will be leaving out, and we will be getting this as a major product. Then what is happening in the third step, in presence of ammonia and isopropanol, this nitrogen lone pair will first attack over the center, and this will leave out, and then again nitrogen lone pair will attack over the center, and this bromine will leave out. So the correct answer is option B. It is a three-step reaction. So this type of reaction basically we can use for the synthesis of piperidine derivatives. Moving to the next question, the major product of the reaction, that is here this compound we are treating with this trifluoroacetic acid and K2CO3 in ethanol in the second step, which will be the major product. So here I think this example we have already seen earlier. So here the correct answer is option A. So here what is happening is that first in the presence of this trifluoroacetic acid, this bond will attack over this center and this will take up a proton, which will result in the formation of this particular carbocation. Then in the presence of this K2CO3 and ethanol, this OH minus will go and attack this carbocation to form this particular compound, that is this one, option A. So this is an example for Prince reaction. Moving to the next question, the major product of the reaction. So this cyclohexanone, the cyclohexanone we are treating with this sodium nitrate and HCl, which will be the major product out of this four options given here. So here what is happening is that first in the presence of this acid HCl we are using, this will get protonated and it will form this particular enol. That is first this enol is being formed, here double bond and here OH. Then NaNO2 we know it is a source of this N triple bond O plus. So once the oxygen lone pair will fall back to here, this double bond will go and attack this nitrogen and this bond will shift to here, stabilizing this positive charge to form this intermediate. Then what is happening is that one proton shift is actually happening, not proton shift. So basically this proton will a proton will leave out and that bond pair will shift to here and this will take up that to form this hydrogen bonded oxide. So this is the intermediate we are getting in this reaction. Then upon hydrolysis we will be getting this compound as the major product. So the correct answer is option A. So we can say this is an example for the nucleophilic attack of enol to NO plus to form the unstable nitroso compound, which which undergoes the formation of oxime, which is stabilized by this intramolecular hydrogen bonding, and the hydrolysis of this oxime will be giving this diketone product. Moving to the next question, the major product of the reaction, this particular compound upon treatment with this methyl sulfonic acid, methane sulfonic acid at 90 to 95 degrees Celsius, which is the major product. So here, this is an example for intramolecular Friedel-Crafts acylation. Yeah. So this starting material is given here. So once this bond will attack over this carbon, that OH group will be leaving out and we will be getting this one and then aromaticity is retained. So this is an example for intramolecular Friedel-Crafts acylation. Moving to the next question, the major product of the reaction, this particular methyl indole derivative on treatment with this acid chloride and this diethyl aluminum chloride in DCM at 0 degrees Celsius, which will be the major product out of these options. Okay, so this is also an example for Friedel-Crafts acylation reaction. So first, this particular compounds, this acid chloride and diethyl aluminum will be forming this acylium ion, which is the intermediate for the Friedel-Crafts acylation, and then this double bond will attack over that acylium ion, and this bond will shift to here to form this intermediate, and then proton elimination will be occurring to deprotonation will occur to give this compound for regaining aromaticity, and this is an example for Friedel-Crafts acylation. Now moving on to the last question of week 3 assignment. So here also this acid chloride and zinc oxide they are using. So this is also an example for zinc oxide catalyzed Friedel-Crafts acylation reaction, where this acid chloride will come this position, that is this carbon will be attacking over this carbon and Cl minus will be leaving out. So we will be getting this compound as a major product, which is option C. So in week 3 assignments, mostly we have seen the questions related to Prince reaction and Friedel-Crafts acylation reaction, intramolecular as well as intermolecular. And also we have seen today the reactions of organocopper reagent, organozinc reagents, Riffermatsky reaction, then uh, what are the Gilman reagent reactions, and Ritter reactions. So I hope this session was useful for all of you to recall all the topics of week 5 lectures and to understand more thoroughly the mechanisms and how to approach the problem by seeing the reagents and reaction condition. So that is all about this week 5 tutorial session. So we will see you in next week tutorial session. Thank you for joining. Thank you for listening. Thank you.